Okay, this is about the normal distribution. My cycle journey to work is 3 kilometers and my cycling time in minutes, if there is no delays or are no delays, is normally distributed with a mean of 15 minutes, mu is equal to 15, and a variance of sigma squared equal to 1. Okay, now I actually included these bits extra just because this is the thing that catches people out, that the variance is the standard deviation squared. So in this case, it's not so identifiable because the mean is 1. Or sorry, the standard deviation is 1 and the variance is 1. Okay? So find the probability that if there are no delays, I get to work in at most 17 minutes. Okay, so this is a straightforward enough one, really. Let x represent the cycling time without delays. Now, we'll get back to the business of delays later on. But just make a little statement like this, that x is normally distributed with a mean of 15 and a variance of 1. Just at the top of your exam paper, just sort of just before you're about to start talking about things like x, just say what x is at the top of your exam paper. It's just an important procedural thing. Don't just assume the lecturer or the person correcting the exam knows it. So what is the probability of the journey time being less than 17 minutes or no more than 17 minutes? That's the probability of x less than or equal to 17. So in the normal distribution, what you would do here with most of these questions, or nearly all these questions, is you would calculate a z-score or use the z-score formula in some way, shape or form. Okay, so the z-score corresponding to 17 minutes when x is normally distributed with a mean of 15 and a standard deviation of 1, it's 17 minus 15 divided by 1, and that gives us a z-score of 2.00. Just in light of writing it out with collecting or finding out what the answers to probabilities using statistical tables, I would normally write it with 2 decimal places. Although in this case, I actually use statistical software as well to actually get these out. I use the R programming language myself for these actual answers. But so essentially, statistical tables might be the way you'll be doing this. So you should be getting answers close to what I get. Okay. Probability of x less than or equal to 17 is equal to the probability of z less than or equal to 2. So this here is the phi function, which is the cumulative distribution function, the CDF of the z distribution. Okay, so that should be in the statistical table somewhere. Okay, it's the phi function. Okay, that's actually a different tutorial, really. That's a whole different kettle of fish there. So phi of 2.00 from statistical tables, that is 0.9972, and here phi denotes the cumulative distribution function of the standard normal distribution. Okay, from statistical tables. Okay, now I will actually use our outputs from statistical computing later on, but so I just mentioned the tables there. Okay, so part B. On my route, there are 3 sets of traffic lights. Each time I meet a traffic light, I'm delayed by a random time that is normally distributed with a mean of 0.7 and a variance of 0.09. Okay, not that it's relevant in this case, and in fact we won't use it, but just to remark that the standard deviation there would be 0.30 if you were to use that for a z-score type question. But we're not actually, as it turns out, but just watch out for that. These lights operate independently. Find the probability of my getting to work in at most 17 minutes. Now there's 3 different scenarios here, including the one we've just met where there is no delays. So altogether it'll be 4. So if just one set of lights is red when I reach it, okay, and the other 2 are green. If just 2 lights are red when I meet them, and if all 3 are red when I meet them. Okay, so this question actually works the same way in each of the 3 occasions. What we're going to do here is we are going to update our mean and standard deviation of our total journey time. Okay, so we have 3 scenarios here: 1 red light, 2 red lights, and 3 red lights. And in each of the cases, what we're doing is adding 0.7 to the mean from before for each red light, and 0.09 to the variance, again, for each red light. So here, what we're doing is, the mean gets added by, or it gets increased by 0.7 for just the one red light. Here by 2 red lights, so it's another 1.4, which brings it up to 16.4, and down here it is 17.1. So all 3 red lights, a mean of 0.7 for all 3 red lights. So that brings us up to 17.1. Okay, and we do the same for the variance, 0.09 for each red light in each scenario. So essentially in this one, there's 1 red light, so we add 0.09 to 1. Okay, and what we do there is, remember, just to get the square root of that, because that is a variance. You essentially add the variances, but we're using the square roots or the standard deviations in the formula. So remember to get the square root. This is the standard deviation here. Okay. Likewise here, 2 red lights, so we increase the variance by, the variance is increased by 1.8. So that brings us, 0.18, and that brings us up to 1.18. The standard deviation, therefore, is 1.0863. Okay, and so on. So essentially what we're doing here is calculating the z-scores using updated means and updated standard deviations. Okay, so essentially what we have here is 3 phi functions, and these correspond to the 3 probabilities for the 3 scenarios. So the phi function of 1.245, the phi function of 0.552, and the phi function of minus 0.0887. Okay, using the tables, you should get these 3 answers here: 0.8934, 0.7096, and 0.4646. Or you should get answers close to that. Okay, if you're using tables, you should get an answer very, very close to those numbers there. They're good enough. Okay, so that's the answer to part B. Okay, and essentially the trick there really is adding the mean and variance for up for each red light encountered in each of the 3 scenarios, and then z-score and then probability. Now, suppose that for each red light, the chance of delay is 0.5. Deduce that the mean value of t, my total journey time, is 16.04. This one is where you have to use all of your statistical knowledge. So this is one where you would sort of recognize that this is a binomial distribution. Okay, here n is equal to 3 and p is equal to 0.5. That doesn't come out easily or automatically, so it's deliberately kept vague, but you just have to sort of try and tease it out here. This is actually going to be the tougher parts of this question here. Okay, so the number of delays is distributed binomially as with a mean there of 3, or n equals 3, and the probability p equals 1/2. Okay, now just to give you a shortened version of it, it's like you should be able to know these ones off by heart in your head if you're familiar with the binomial distribution. So the probability of meeting no red lights is 1/2 times 1/2 times 1/2. Okay, so it's 1/8. There's 3 different ways that you can encounter 1 red light, 3 different ways that you can encounter 2 red lights, and 1 way that you can encounter 3 red lights. So essentially it works out that way. It's like a coin toss experiment. The probabilities of the 4 scenarios are 1/8, 3/8, 3/8, and 1/8 respectively. Okay, so where do we take it from there? This actually turns into a discrete random variable question there. So the expected value of t is essentially the sum of t times the probability of that t. Okay, if if that's in shot there. Yeah, discrete random variables. So here's our values of t and the probabilities of those expected times for each of the 4 scenarios. The no delay, no red lights, the 1 red light, the 2 red light, and the 3 red light. So essentially what we do here is, discrete random variable. We have 4 scenarios. The probability of that scenario times the mean value of that. Probability times the duration. Calculate, add them all up then, and then just simplify, and you should get 16.05 minutes. Okay. So this question, this part was actually quite easy, really, but it's just actually sort of like thinking it through and sort of not just thinking this is going to be a normal distribution question only. At this level, expect other sort of things to come into play, like the discrete random variables, the binomial, maybe in other questions, Poisson and exponential. So just sort of be ready for that sort of thing. Whoops. Okay. So finally, one last part to go. Given that the variance of t bar equals 1.5025, use a suitable approximation to calculate that the probability that over 10 journeys, my average journey time to work will be at most 17 minutes. So this is a sampling distribution question, really. Okay. So we're not asked what the probability of a journey time being less than 17 minutes. We're asked what's the probability of 10 journey times having an average of less than 17 minutes. Okay, so sometimes you might have 17-minute journeys, 3 or 4 of them as part of that 10, but really what would happen is that some other shorter journeys would cancel out, so that the probability of having an average of greater than 17, what is that? So the mean time, we know from the past, in the last question, was 16.05. Okay, so we're just using previous parts. We know that the variance there is for the past question there is 1.5025. So this is the sampling distribution variance here. So it's the variance of t bar over n. Usually that's written as the variance of x over n. Okay, so actually that should be a t bar there. Anyway, so that should be capital T there. There should be no bar on that actually. So anyway, so that works out to be a very straightforward normal distribution question. Z-score, 5 function, tables, there's your answer, 0.9929. All right, so yeah, that's it there. Leave it there.